thanks to the lockdown, I've been able to film this video from the hearts of the Amazon rainforest. Look, there's a wild animal in the middle of eating in its natural habitat.
Hey, that's mine. What are you doing?
Different people would break down this animal food to different levels to find out what it's made of. An animal researcher would break it down to molecules or even atoms. A particle physicist, however, would break it down to the smallest fundamental particles. And inside this green mango might just be a green particle, but nothing to do with conventional color.
Confused? Let's break it down further. If you were to expand an atom, you would get a proton, electron, and neutron. In a proton or neutron, you would find three colored fermions. The fermions are held together while they zoom near the speed of light. Now, there are two questions that arise. How can three fermions exist in a baryon? And what holds these fermions together?
The first question doesn't really make sense, or at least without Pauli's exclusion principle.
Pauli's exclusion principle says that no two identical particles can occupy the same space. So, a baryon like a proton or a neutron cannot have three identical fermions. So what's the problem? Let's take the delta baryon for example. Delta baryons are made up of three up fermions, and each fermion would need to be different. With a plus half or minus half spin, two fermions are still identical. With color charge, however, taking the analogy of light, we can give them a red, a blue, and a green charge, and together these colors would make a white or colorless baryon. The fermions are held together by the exchange of particles called gluons. The gluon's anticolor makes the fermion colorless, and then the fermion gains the color of the gluon. And now the baryon looks like a disco ball.
Without quantum color, chemistry would be extremely different, and our world could look like something out of a science fiction movie.